Hello and welcome to Crave the Wave. This is Electromagnetic Waves and Light, Class 3. My name is Russ Burleson and my email is provided. This is provided to you by the National Science Olympiad for help in doing this event this year. So today we're going to do a quick binder check, go over some homework, and then we're going to do an electromagnetic wave review. So we're going to cover everything from the waves to what the electromagnetic spectrum looks like, particle and wave properties, speed equations, reflection, refraction, diffraction. We'll go over that, and they'll be confusing at first, but trust me, after a while they'll make a lot of sense. We'll talk a little bit about superposition and interference and polarization, and then we'll create some homework for the next class. So get out your binder. Remember, same rules applied as last time. You have 10 seconds to find all this stuff. If you can't find it, then you need to work on your binder. Okay, and that might be reorganizing, might be putting in new tabs, etc. Or you need to add stuff. So in your binder, find the speed of sound in air at sea level and STP. Make sure you're not just memorizing it, but you need to be able to find it. Okay, very good. What is the speed of sound as a function of Kelvin, and what is the speed of sound as a function of Celsius, degrees Celsius? Two separate equations. I'd like you to also find what speed is Mach 2 at 10,000 meters. So we got an airplane flying at Mach 2. It's a jet plane. It's a fighter aircraft. All right. It's going pretty nice altitude, and it's going Mach 2, which is really moving it for a jet plane. What speed is it going in meters per second? What is the bulk modulus for steel? Hopefully you've got other materials, but you definitely should have steel. And then the last one is, what's the equation for the sound of speed of sound in steel? See if you can find it, or even better than that, see if you have a general amount that the speed of sound in steel should be. Okay, these were just some examples of some of the types of things that I might be asking you to find very rapidly in your binder check. So let's talk about electromagnetic waves. So now we're talking about waves that are based on energy, okay? And what happens is that you'll notice here we have an electric wave and we have a magnetic wave. So the electric wave is shown in this diagram by the red up and down along the z-axis. And then you'll notice that we have a blue magnetic wave that is back and forth along the x-axis. But the direction of the wave is along the y-axis. Okay, so you'll notice one thing, it's a longitudinal wave because both the electric and magnetic fields are perpendicular to the direction of the wave. Okay, but it's really important to notice this, that for there to be an electromagnetic wave, there has to be both an electric and a magnetic component. Because one causes the other and the other causes the other, they have to work in concert with each other. And the direction of the wave will always be perpendicular to both. Another fancy term for this type of three-dimensional perpendicularness is called orthogonal. Okay? So, electromagnetic waves have energy. So the electromagnetic spectrum is the name scientists give to the different types of radiation that exist in the physical world. Okay, sometimes it's going to be very, very low, like radio waves, or might be microwave or radar waves, might be infrared, might be visible radiation, which we can perceive with our eyes. And by the way, that's what determines the upper and lower part of visible, is how good the human eye works. Dogs have a different visible spectrum. And then above that spectrum is ultraviolet, and above that is X-ray, and above that is gamma rays. And gamma rays includes all sorts of things, including cosmic rays. But what you'll notice is that the frequencies go up really, really high. So we go from 1,000 here, if you will, hertz, all the way to, 10,000 hertz here, all the way to 10 to the 20th So that's 10 with 20 zeros for gamma rays. And you'll notice that the radio waves start out at a kilometer here, and they go all the way down to a picometer, and even smaller. Okay? And so the thing that I want you to keep in mind is that wavelength and frequency are inversely proportional to each other, so as one's going up, the other one's going down. These type of electromagnetic spectrum graphs are exactly the type I expect you to go grab, but just please grab as many as you can from Wikipedia, from physics books, from images.google, as many as you can. So let's talk about that spectrum. The number one thing I want you to keep in mind is that the speed of light is constant in any single material. Okay, it doesn't need to even have material. It can be done in the vacuum of space and it will travel forever and ever. It's called free space. Frequency and wavelength are inversely proportional to each other. So as one goes up, the other one goes down. And you'll notice we talked about it: radio, microwave, infrared, visible light, ultraviolet, X-rays, gamma rays. That's as we go up in frequency. Okay, and there's a whole bunch of different ways that you can show this. And then one of the things that they'll quite often do is that they'll give you references, like their wavelengths are the size of buildings, these wavelengths are the size of people, these wavelengths are the size of atoms, and these wavelengths are the size of atomic nuclei. Okay, so it gives you an idea of the scale of things. Now keep in mind, some frequencies transmit through the atmosphere with less loss. And what you'll notice here is here's a diagram here that shows you that basically all of these frequencies here do not transmit very well through the air. Okay, various parts of the atmosphere, whether it's water or oxygen or other things in the air, tend to absorb the energy, and they don't transmit very far. So these areas where you have low transmission are these little windows, and these little windows are where you can have things like radio stations, TV stations, radar systems, where we can actually see light. Okay, and so what you'll notice is that that's why the spectrum is so coveted and monitored by governmental agencies, is because they want to have specific things at different frequencies. You need to have several versions of the spectrum throughout your binder, and you'll notice here it shows the transmission, and where you can transmit very easily here, you can see very easily here, you can transmit here. But you'll also notice here it has the same thing with yes, it will transmit, and then of course it will have no, it will not transmit right here. So let's talk about electromagnetic waves. Are they a particle? Are they a wave? And the answer is yes, they are both. Okay, so wave-particle duality means that everything has both a particle and a wave nature, but electromagnetic waves really do. Okay, so like the particle of light, which is one of the main types of electromagnetic radiation here, is given, it acts like a photon. And a lot of times it's absorbed like a photon, it emits like a photon, it emits like a single item, or a quanta, if you will. All right. But it also acts like a wave because it's got a wavelength. And there was this guy named James Clerk Maxwell who is very famous in physics and other circles. And he developed basically a group of equations. He tied them all together, and they're called Maxwell's equations. And two of the main ones talk about how, like, changing electric fields induce a magnetic field changing. One's changing over space, the other one changes over time. And you'll see here, this is like the change, this is a fancy mathematical way of saying the change in space of an electric field is going to cause a change in time of the magnetic field. And the change in space of a magnetic field is going to cause a change in time of the electric field. Now, here's the number one thing I want you to take from that. I just gave that as an example. This is not to show, this is only showing the equations. It is not ever, you will never have to do this level of math. This type of math I didn't learn until I was a senior in high school, or actually even much later. Okay, so the thing I will tell you all is do not worry about this math here, but just remember that the change in the electric field causes the change in the magnetic field, and the change in the magnetic field causes the change in the electric field. And if one's changing over space, the other one's changing over time, and vice versa. So let's talk about the speed of electromagnetic waves. So the great news is, in free space, in outer space, way out in deep space, it's a vacuum. It's also called free space. Everything that's electromagnetic travels at the speed of light, always referred to by c. It's constant. It's 2.99792 times 10 to the 8th meters per second. However, any test I'm ever going to write you, I'm going to go with 3 times 10 to the 8th meters per second squared, because that's accurate to actually like four significant digits. Okay, that is one of the most important things that you should know, and it's actually one of the most important things that you should have in your binder. Now, the speed of light in any other material is going to be less than that speed. There are some funky types of plasma materials where we can have like it look like we are going faster than the speed of light, but that's because of the difference in phase and group velocities. So don't worry about those special cases. But basically, there's what they call a refractive index of a material. And what you want to think about is that, just like, remember how density kept showing up all the time when we were doing those pressure equations, we were doing the sound equations. The refractive index, or the refractive indices, are very similar. And so like air has got a refractive index, water's got one, steel's got one, everybody's got, every material's got one. Now, the most important ones are the ones that are transmittive, okay? Because something like steel, you can't actually shoot light through steel. It dies off pretty quick. It has a very small skin depth. But you can, however, shoot light through a plane of glass, or through water, or through, let's say, silicon dioxide, okay, or through a fiber optic cable. And so some of the sample indices, okay, air, you'll notice it's not 1, but it's close. Water is actually significantly different. It's 1.333. So in other words, it's like with an extra third on top of it. Cubic zirconia, which is fake diamond, is 2.15, and real diamond is 2.42. And that's one of the ways that they can do a cubic zirconia test to figure out if something's cubic zirconia or diamond real fast, is they look at the different indexes of refraction. Okay, and so now you can also, if you have the permittivity and permeability of those materials, okay, you can figure out what the speed of light is in any material. Okay, and it's 1 over the square root of the permittivity times the permeability. Now, the permittivity and permeability of like free space are given by epsilon 0 and mu 0, and you just put those in there, and then you've got the speed of light in free space, which is this 2.99792 meters per second times 10 to the 8th meters per second squared. But you can also, if you have those constants for that material, you can determine the speed of light, and the speed of light will apply for all electromagnetic radiation going through that medium. Okay, so you can easily see it's a good idea for all these things that you might be having electromagnetic waves go through. You're going to want the refractive index, but you're also going to know the epsilon, and you're also going to want to know the mu. So let's talk about reflection. So there's a law of reflection where it says that the incident angle, here given by theta sub I, is equal to the reflection angle, which is theta sub R. And so what you'll notice here is that if P shoots an electromagnetic wave at a perfect mirror, okay, it's perfectly polished, the bounce back will be exactly the same. So theta sub I, the incident angle, is equal to the reflective angle. You'll notice they're both off of what they call that perpendicular or normal of the mirror. So here we have a mirror, and you'll notice we have a light source here, and you'll notice you got theta sub I and theta sub R, and the numbers are exactly the same. And so in this case, we are right at 45 degrees. 45 degrees in, 45 degrees out. Okay? Now, that type of thing off of a perfectly polished mirror, and you'll quite often see that on like really flat, we call it water, or sometimes you'll see it on something that's just very, very shiny, okay, like a mirror. That's called specular reflection, and it's exactly equal. However, non-smooth rough surfaces also exhibit a reflection, but it's called diffuse reflection. And what it means is that when you have a rough surface, okay, like let's say the paint on this wall here, okay, you'll notice that at the top, right above my head, is a very bright section. That's the specular reflection, okay? So I've got a big light right up here, and it's bouncing off this back wall and bouncing to the camera, okay? And the specular reflection here is where most of the energy is going to be, or it will be shown in this blue light. But because the paint is not exactly perfectly flat, we also get a lot of diffuse reflection, and that's how you're able to see the rest of the wall. It's because it will hit those sections and it'll still bounce right towards the camera. Okay, so pretty much anything you see other than a mirror or something that's acting like a mirror, like a flat piece of water, like a still lake, is going, or like a reflection off of glass that sort of blinds you or whatever, okay? And that's the reason why it blinds you, is because it's the most intense. So like you look at my cell phone, you know, it's a rough surface. You can still see it, and that's because you're getting diffuse reflection off of it. We also have refraction. Okay, and so what refraction is it's sometimes referred to as the bending of light. And what happens is you remember how I said that the speed of light is constant in any one material. But if I have two materials, it's actually, and they have different indexes of refraction, they're actually going to have different speeds of light. And what that means is that when the light goes through it, okay, different wavelengths will have different effects. Okay, and what you'll notice here is that we have a velocity in interface one, in media 1 here on the left, and on the right we have a different medium, okay, which has a different index and a different velocity. Okay, and you'll notice the light actually bends, and you see the motion here below where we're changing from the blue to the green, and you'll notice that it, you know, the light does tend to bend, okay, right at that surface. And because it bends differently for different frequencies, we can take white light through a prism, and if we make the prism exactly right, we can actually bend that light differently such that we can create the rainbow. Okay, now if we've got the same material on two sides of the same thing, like in this particular case we have a plexiglass block, you can actually see the light come in, bend, and then bend back. And this is why sometimes when you're looking through thick glass, or you're looking into something, something can actually appear a few inches to the left or a few inches to the right or maybe a few inches up or a few inches down from where it really is. Okay, it's because of the way the light comes in. Now this is very hard to see, but what I'd like you to look at is that if you look at the light going into the block of material here, you will notice, okay, that the light comes in here as an incident, and you have the reflection. By the law of refraction, this angle here is equal to that angle there. And this angle here looks to be about 50 degrees. Or actually it's not 50 degrees, it's 30, 40. Yeah, it's 30 degrees, sorry. And this angle here is about 30 degrees. But then we have a refracted angle, and you'll notice it's opposite sides here. And so this part here is refracted, and this part here you can just barely see it as reflected. Okay, so yes, you can actually have the light split, and that sort of makes sense because if I'm shining a light on top of, like, let's say a lake, I can see the reflection up. But what I can also see is if I'm in the lake, I can also see the light inside the lake. So a guy named Snell came up with his law for a given pair of media. And basically the ratio of the signs of the angle of incidence and the angle of refraction is equal to the ratio of the phase velocities, the ratio of the velocities. Okay? And so what that means is that if I look at this, the ratio of the signs is equal to the ratio of the velocities, and that's inverse equal to the ratios of the indices of refraction. Okay? So this right here is all Snell's law. So whenever you have two media and you have light going through it, this is how you can figure out what the differences are in the velocities. And this is also how you can figure out the differences in the angles. Now keep in mind, there is an angle at which basically you get a trapped wave. So if you notice through a normal thing, and by the way, usually if you're perfectly normal, you won't be anywhere near the critical angle. But basically what you'll notice here is that at a very steep angle, okay, we've got light coming from down here, it gets refracted, it gets bent, okay, and it goes out. However, if we keep increasing this incident angle, at some point the light gets bent so much that it's going along the surface, and it's a surface wave, it's a trapped wave. And then if we keep increasing the incident wave beyond that, it actually acts as a mirror again. We now have total internal reflection, and we follow the law of reflection. So why is that important? So I don't know if you've ever noticed, if you're in water and you're at the bottom of the pool and you look up at the top of the pool, you can see stuff above the water directly above you. But if you look at the end of the pool and you try to see something above the water at the far end of the pool, you can't see it. And that's because it's below your angle of incidence is greater than the critical angle, and you have total internal reflection. And so they'll quite often use the thing of the fisherman is at this location, can the fish see the fisherman? And it's basically trying to see what is the angle, if you will, by which the diffraction would actually still be able to see the fisherman. Okay? And so this is used quite a bit in types of problems like that. So remember, refraction will always have two separate medias, whereas reflection, it could just have air and a mirror, or it could have air and, like we talked about, like in this particular case, you can have reflection anytime you've got another surface you're bouncing off of. The third way that waves sort of get around things is diffraction. Okay, so the diffraction now is the bending of the waves around corners of an obstacle, sometimes through an aperture, sometimes through what we call a shadow boundary. And basically, this isn't because we have two different media, it's because we have a structure. So if I look here at ocean waves, the ocean waves are coming in this way, and we've got like a little slit. We got a little area where the energy comes out, and then they circulate out in almost a spherical or a circular form directly from that area. So even though the wave, if it's coming this way, never gets here, okay, it will come in here and bend around. Now, you can also do that with multiple slits, and you get these interference patterns like you see here. You can also do it with like shining a light through a pinhole, like in this particular case, they're shooting a helium neon laser through a pinhole, and again, you get diffraction and circular patterns. Okay, but another really one of the areas that I like to talk about, just like we were talking about, hey, can the fish see the fisherman when we were talking about refraction, for diffraction, is that it will bend around a shadow boundary. So in other words, let's say somebody's got a flashlight. And they flash a flashlight on like a column, and you're hiding on the other side of the column. You're not in total darkness, are you? It's not like if you looked on the ground as you were shining your light at a corner or right at the edge of a column. It's just a straight line, like this part's illuminated and this part's dark. There's a little part in the darkness that looks like it's bending, and it really is. The light is bending around that corner because there's a difference in that shadow region. Okay, and so this is why if you hide and you're close enough to the shadow region, you can probably be seen a little bit. So now let's talk about the next topic. So let's talk about electromagnetic superposition and interference. So the superposition principle, and this applies to all linear systems, which is all systems that can be added and subtracted. That basically you can add up any phenomena that follows superposition principles, which all waves do, means that you can add them on top of each other and they will either add or subtract. So what we'll notice here is that we have a red and a blue wave, and they're of the same amplitude. And sometimes they add, and that's why the observed wave, this black wave, is sometimes higher than both the red or the blue, because they're adding. But sometimes it gets down here to zero, right? And the reason why it's down to zero is that you'll notice that about this point, the red and the blue are always opposite of each other and equal. So sometimes they're going to be what we call, and by the way, this is how interference occurs, okay? And sometimes they'll be adding to each other, and that's called constructive interference. And sometimes they'll be subtracting from each other, and that's destructive interference. So if you look here, here's an example of constructive interference. We have waveform 1 and waveform 2. They're both exactly the same, but the combined waveform looks like a double amplitude waveform, the same waveform. That's constructive interference. Destructive interference, they're exactly out of sync, just like we are at these points here, and it looks like we have no waveform. So if you ever hear about noise canceling headphones, that's what they do, is that they have little microphones receiving the sound that they perceive to be noise, and then they broadcast the inverse waveform. It's sort of like an active noise suppression. Now let's talk about polarization. Okay, so polarization is something that we talk about with transverse waves only. We really don't talk about longitudinal waves because they don't really have a vector. They're just scalar usually. They specify the geometric orientation of the oscillations. Simply put, what that means is that if you look over here in this particular case, the electric field is in the ZY plane. It goes up and down Z. So it's linearly polarized in the Z plane. The magnetic field is in the XY plane, and so it is linearly polarized in the X plane. So this would be what we would call a linearly polarized electromagnetic wave. However, let's go back to our superposition concept, and let's say I had one wave that was exactly orthogonal to the other. And if I get them exactly in sync, I can actually create what's called a circular wave, a circularly polarized wave. And a circularly polarized wave can be broken down, as you'll notice, into their linear components. So this is, you can break down any of them into two linear polarized waves. One thing that's really neat is that polarization allows us to apply filtering technology. So sometimes we can ignore things we don't want to see. And what they'll do is that, like polarized sunglasses, they filter the polarization from specularly reflected sunlight. Okay? So what it does is that it filters out anything that would be bouncing and would be specular. So in other words, anything that'd be bouncing off a mirror, like a lot of times water can act like a mirror. You get a lot of specular reflection on thing, and it cuts down all the glare. And oh my gosh, you can see so much better because it gets rid of all that stuff that's blinding you. Okay? And one of the things that really helps in that is that sunlight is actually scattered as it goes through the atmosphere by all the aerosols in our atmosphere, by the ozone layer and such. So what that means is that you can see the blue sky without getting blasted, if you will, by the sun itself. Radio stations and normally use vertical polarization, and TV stations normally use horizontal polarization. Okay, this can even in some cases allow you to use the same frequency without interfering with each other, because you can orient your antennas differently. You can also do conversions. So like what you'll notice here is that they have a machine that is making the rubber band go around and around in a circular wave. It goes through two small flats and it turns into a linearly polarized wave. And think about it, if I have a linearly polarized antenna and I can take out of the circular polarized signal just either this linearly polarized item or this linearly polarized item. And so sometimes you can use that to split a waveform. So let's talk about homework. I would like you to put all your various formulas for speed of light, Snell's law, law of reflection, critical angle, etc., and the wording for Maxwell's equations that makes sense to you. And here's why I mean the wording for Maxwell's equations. You're going to look at some of the descriptions of Maxwell's equations, and they don't make any sense at all. Look for a different one. The reason why is the only question, they can't ask you to solve Maxwell's equations, but they may ask you, hey, if I have a varying electric field in space, what does that induce? And it's a varying magnetic field in time. Those types of things are going to be what they're going to look for. Get at least 10 spectrum charts in your binder. Remember, last time I asked for 3, now I want 10. So this is like 5 pages of them. Personally, I wouldn't stop till I got to 20. Find out what the speed of light in free space is. Okay? Make sure you put in there the equations, etc., because I'm going to be asking you what the speed of light in water is. I'm going to be asking you what are the table of indices of refraction for common transition materials like air, glass, water, crystal, diamond, quartz, etc. anything that I can transmit light through or an electromagnetic wave through. Okay? It would probably be also a good idea to have that permittivity and permeability. So that's class 3, and continued good luck.